maybe a Rush song would be some good theme music for the program. Hey, so it is Thursday, March 5th, and I thought we'd just today go over a little bit of phasor sums. And I think what ends up being confusing, and I'm learning this a little bit as I go, but it's difficult sometimes to go from just the physical reality of the system. Okay, so you've got a motor with a bunch of wire wound around a magnet, to the funny little AC diagram, and now you got this weird delta versus Y three-phase thing going on. So let's just coalesce those ideas into one nice explanation. And Ryan, I thought we'd just go over that one problem.
I have the book if you want to look at it.
I got the book. All right, so let's back up from a couple weeks ago, and first I want to talk about the fact that the dE dx, and it's a little more subtle in this, but the direction in which the electrical field is pointing is in some way proportional to dB dt. And that's the rate at which the magnetic field is changing. And just for simplicity, what I want to do is show, instead of an electrical field and a magnetic field, I just want to show it on a bicycle. So I think that'll be a lot simpler, but the physics are exactly the same. So here's your bicycle. I think I told the joke or the prank. Yeah, I took my fraternity brother's pedals and put them at 90 degrees, and it was really hard to ride. But on a bike, I mean, if you don't have clips, really the only way you can push is sort of down, right? You can't really pull up, you can't push forward. So the force, if we just look with the left leg, and let's just say this is the left leg pushing down, your right leg's over here. At the very top, I'll just draw the top as a little, at the very top, you're pushing down, but you're not making the bike go at all, right? You're just pushing down straight into the crank arm, and it's not moving. So let's look at this as sort of, top, dead, center, which is where this is, top, dead, center. And if instead of volts, we look at force, and if you can remember from the discussions before, both force and volts are our across variables. So I'll just put force up here, comma, volts. There is none, because you're pushing straight down, and you're not doing anything. But I think you can appreciate that when you are, let's just call this 90 degrees out here. When you're at 90 degrees, your force is maximized. Well, it's not your force it's actually your torque that's maximized, right? I mean, you're still pushing just as hard, but you're not doing any work because you're top, down, center. And then again, you get, we'll just call this bottom, dead, center. You're again back to zero. Well, I've drawn 3 points. As it turns out, those 3 points are connected to a special kind of curve. What kind of curve might that be? Sine wave. There we go. So now with the left leg, we're going to have to wait. We're going to have to wait another, well, until you get all the way back up. So here's bottom, dead, center. We'll call this 270 over here. I know I'm drawing it backward, that's okay. Here's your 270. And that you're still at zero, and you're still at zero till the time you get back over again to top, dead, center, and it's not there until you sort of pick it up again, right? And so, in some ways, well, what's going on over here, this is actually going to be your, so if this is your left leg, this thing that I just drew and dashed is sort of your right leg. Your right leg is doing something too. So there's sort of this dead zone in there. Now the same exact thing happens in an electric motor, and I've written up the equation right here. And just to go back to it, I'll go back to, and I'm having all kinds of trouble connecting today.
Yeah, it's been real.
Yeah, so let's just skip that. But if you remember, I just brought up the Wikipedia page on Maxwell's equations. And we talked about the fact that the electrical gradient is perpendicular to the magnetic field. And it's very similar to the bicycle that I just drew, in that if during the cycle, if those two fields are lined up, you're doing work, you're pushing. If your electrical field is aligned with your magnetic field, perfect, you're doing work. If not, if you're 90 degrees out of phase, you're out of luck. Difficult to visualize, but that's where we are at that. The next thing to think about is the three-phase power, and I'm going to try my best to draw that. I think I've got an Excel kicking around somewhere, but I'll just do my best to draw it. Good practice. So where's 120? There's 90. Here's about 120. I'm just going to take and do something like this. It's going to get sloppier the further right I go, but then I'm going to go another. So there's 120. I got to go to 240. There's 360. Let's see. There's 180. 270. I'm going to start in about here. I kind of, the right-hand side, don't worry too much about that, but if we go like this. Okay, so from peak to peak, well, from here to here is 360 degrees. Same thing, red peak to red peak is 360, green peak to the green peak is 360. But from, or I'll say comma 2 pi, right? Same thing. From here to here is 120 degrees. What's that, 2/3 pi?
120?
Yeah, 120 I think is 2/3 pi. Because 180 would be pi. And then here's another 120 peak to peak, 2/3 pi, same thing, 120 degrees, 2/3 pi. Okay, so there's your three-phase power. Talked a little bit about how that is similar to a wind turbine blade. Talked about why it's important that you kind of keep those guys. And so what this does, this is a little bit, if we go back to the bicycle analogy, it would be a little bit like having a triple bicycle, 3 people in line, and each one of the pedals was 120 degrees. And so instead of like sort of these thrusts of power, it just smooths it out. That's what we're thinking about there. Okay, now let's look at the sum of 2 waves that are both exactly in phase. So let's just say we've got here, let's just say this is like a 110 volts. And we'll just take that 110, copy, paste, oops. Copy, paste. And we'll just add them, get them right in line with each other. What happens if I add those 2 guys together? I'm basically just doubling it. I'm just doubling the amplitude. So I'm just going from something that's 110 up here to 220. They're still exactly in phase. So I've come down through here, come up through here, come up through here. Okay, and the way to write these, let's just write them out mathematically. The voltage as a function of time equals, and remember, you need two components. It's because you look at it's kind of a two-dimensional picture, isn't it? Well, it is a two-dimensional picture. I drew it in 2 dimensions. So any two-dimensional picture, you just need two things to describe it. Actually 3, but we'll get to the third in a second. The first is just the amplitude, how tall it is. That's what this is. 110 volts equals the amplitude. The other thing you need, well, we've already determined that's a sine wave, that's the function. The other thing you need is the frequency. Higher frequency, the waves get closer together. Longer frequency, they get further apart. Times the time. Can't do anything about time. So this is chunk number 1. The frequency is chunk number 2. What's the third thing you might add in there? To mix it up and spice it up a little bit.
Oh, how much is out of phase?
Just the phase. Just the phase. So I kind of lied and said it's only 2 parts. It's actually 3. Plus the phase. If I wanted to turn that into a cosine, what would I do? What would that phi that I just wrote equal? Well, hopefully there's some. Well, just take a wild guess. Wild guess. What should phi equal to turn that into a cosine?
Oh no, man.
Just throw something out there. The price is right.
What should that angle be?
What should the angle be to turn the sine into a cosine?
180.
I hear 180. Let's keep guessing. Could be right, could be wrong. I don't know, but it's a good guess. I mean, it's a reasonable guess.
0.
Got a 0.
Well,
Here's your sine wave. It's all right. Here's your sine wave. Here's your 0. Here's your 90. Here's your 180. Here's your 270. Here's your 360. Or 0. Here's your 90 again. Here's your 180 again. Here's your 270 again. Here's your 360 again. Okay, where on this thing is the cosine? If I were to, yeah. So if I'm going to draw the cosine, I got to start up here. It's going to be 0 here. It's going to be -1 here. It's going to be 0 again there. It's going to be maximized there. 0 again there. Negative there. Dink there. It's the same shape. It's just 90 degrees out of phase. So there's your sine and your cosine. So that's the third component. This guy tells you how big it is. This guy tells you how quick you're talking. And this one just gives you your left and your right. Those are the only 3 things you can do with a wave. Make it taller or shorter, squish it together, or shift it left and right. So those are the 3 components of any one of these waves. And we just determine if they're exactly in phase, meaning that phi equals 0, you got this picture. If phi equals 90, you turned your sine into a cosine. And you could do that in Excel. In fact, let's just do it. Really, really fun, really quick. Fun little exercise. Because in fact, I might have just misspoke. I can't remember if you add 90 or subtract 90, but here's a little computer science experiment for you. Man, this is weird. Okay, so let's just go like so. 0, 90, 270. Now I should be able to hop in here, drag her down. Oh, I skipped 180. 180, 270. try again. Like, where'd 360 go, man? 50, 720. Yeah, now we're kind of getting up there in the snowboard competitions, right? You just do it so. Okay, so here's your degrees. Here are your radians. Now equals radians. There's a radians function, radians of that. Close paren, dink, dink. And just to look at that, okay, that's about pi, right? There's your 2 pi. Now, so we'll run sine equals sine, open paren, dink, close paren, dink, take it, drag it. Fun. If I do a control 1 on that guy, like what the heck is e to the minus 16th? Well, it's about 0. It's the error limit of the computer. Let's turn that into a number, 2 decimal places, fine. So that's your sine function. Here's your cosine function. Equals cos of there you go. Control 1, number, boom. Okay. Now, here comes the experiment. You're like, oh, I can't remember. Is it plus? Is it minus? I just don't remember. Sine plus 90. So we're going to add 90 degrees of phase to it. Actually, let's do it this way. Start a new experiment. We'll start with deg plus 90, right? Equals dink plus 90. Drag that down. Rad plus pi by 2. If you want to get fancy, you can come up here, do a shift left arrow, home, SYMBOL, boom, rad 90 plus 2. Okay, so, and then just the same thing. Take this column, copy, paste, didn't have to type anything, drag that down, magic. See, there's your pi just showed up again. Okay, maybe we'll format that guy too. Control 1, number, 2 decimal places, great. Same thing. Control 1, number, 2 decimal places, perfect. And then just for grins, we'll take the whole thing, home, centered up, looking a little more pro. Okay, so what we've done is just started with degrees, radians, sine, cosine. I shifted the thing over 90, put it into radians. Now I'm going to take the sine of that thing. Equals sine let's check it out. Control 1, number. Okay. Now I can see visually that they're equal, right? I can see that sine plus 90 does in fact equal the cosine. Now, to be a little more pro with this, you'd say check equals this minus that. The way to check whether two things are equal or not is to subtract them. If you get 0, they're equal. Magic. Okay, so the cosine is equal to sine plus 90 degrees. Problem solved. Okay, so we've added two things exactly in phase. We found that the amplitude doubles. All the power systems you're ever going to deal with in North America are always going to be 60 hertz. That's what your omega is. But now, in your three-phase power, what does phi equal in your three-phase power? You might think 60, and in some sense you'd be right. But go back to this first guy, it's always 120. Each one's 120 degrees out of phase. Yeah, because if you had 6-phase power, you could. Big, beefy, juicy motor, lots of torque, 6-phase power, then you'd have it 60 degrees. It's conceivable. So, now comes the fun part. Now we got to get from the machine to the waveform to this weird thing we call the phasor sum. And what we got to do is go from this little arrow. So there's an invisible arrow sort of pointing up right here, right? And there's another one right here. There's another one right here, telling you how tall that wave is. How hard is that thing pushing? And they're right here, and they're right here, and they're all just hanging out right here. Well, when you add them together, let's go black again. Add this arrow right there to this one right here. You get an arrow that's twice as high. So there's a bunch of little arrows hanging out under there. That should be fairly easy to see. The weird thing comes in when we do the phasor sum. What page is this in the book again? We were just looking at it. I want to do that same problem we did yesterday, Ryan. It was the Y. I think it's
111.
111. Perfect. Oh yeah. So let's draw the 3-phase circuit for a Y connection. So we'll start in the middle. That's our neutral. Come out here, come down, all the way out here. There's your N for neutral. Come up here, coil B. Come up here. There's coil A. Come down here. There's your coil C. Now, let's go all the way. And these lines are just, you can imagine these lines as just being the leads on your multimeter. And for now, so you could imagine sort of taking your multimeter and sticking it on the end of any one of these coils. There's those two guys. We'll come down here. We're going to call this one line 2. We're going to call this one up here line 1. We're going to call this one down here line 3. So we've got 3 lines and a neutral, 4 wires total. This neutral will more than likely be attached to ground. Once your magnets and whatnot are spinning in each one of these coils, you're going to get a certain amount of voltage. As it turns out, this particular circuit is designed to have 120 volts between line 2 and neutral. Same deal here, 120 volts between line 1 and neutral. And same deal here, 120 volts between line 3 and neutral. So all 3 lines are at the same voltage, just like I tried to draw with the red, green, and black. They all have the same amplitude. So you're going to take those 3 readings on your 3-phase motor, and there it is, 120. The question is, how do you add those voltages together? Now, it was very simple when everything was in phase. We just sort of looked at it and added the arrows up. It's different when you were in so-called phase space. And so I don't know how far you guys have got into algebra, but I think we've talked a little bit about the fact that you could be in like Euclidean space with X, Y, and Z all perpendicular to each other. You could be in polar space. Well, let me just draw it while I'm talking about it. So you could be in, here's your rectilinear coordinates. Here's your X, here's your Y, here's your Z, and everybody is perpendicular, right? That's sort of one space you could describe space as. Another one would be your polar coordinates. Right, so in this case, z, let's just still let z point up. We're going to let r point out. Only problem, r's pointing out here, r's pointing out here, r's pointing out here. Which way is r pointing? Well, it's pointing out. Now, you got to come up with a third direction that's perpendicular to both up and out. Well, it's this one. It's this circle right here. And we just call that theta. It's just your angle. So we've covered all three spatial dimensions. It's just one happens to be rectangular and the other one happens to be a cylinder. You could keep going with it. Here's the Earth. R is out. What are the other two directions on Earth that we conventionally use for telling you where you are? Give me your waypoint. Give me two numbers. What are they called?
Latitude.
Latitude, longitude. So that one, and the latitude, just a bunch of circles you measure, always pass through the North and South Pole along the lines of longitude, and your longitude is how far east and west you are. So those are spherical coordinates. Still in three dimensions, just different ways of describing physical reality. Okay, so now we got to do the same thing for phasor space. So we're going to take this funny looking equation. Well, it's not that funny looking, it's pretty, this is the voltage as a function of time. And do the same thing. So what we're going to start with is just, like voltage does not point in any direction, right? Voltage is a scalar, but for now, we have to force it to point in one direction because it's either positive or negative as a function of time. So we more or less have space on one axis and time on the other one. Okay, so here we go. And we're just going to go horizontal because that's convenient. That's what's shown in the book. And we'll just let that be, let's just let it be E sub A, or V sub A, or the voltage in line 1. I don't care what you call it. It's just how big this voltage is. 120 equals E sub A equals V sub A. But that's how big the amplitude of that voltage is. Okay, so it's pointing here. Now, if these things were exactly in phase, I would just add another one here, and I'd be done. That's 0. And this is where, I think this is why you said 60 a while ago. This is the confusing part. The next arrow I have to draw is right here. And there are going to, well, let's do a little bit better than that. The next arrow I have to draw is right here. This is 60 degrees. This is 120 degrees. Yeah. That is a confusing thing. Because I would want to take this thing and say, well, if it's 120 degrees out of phase, then it's pointing back here somewhere, right? Why does it end up being more like 60 than 120? Let's think about that for a second.
That is what I thought, so it's 120 degrees out.
Yeah, there's a little bit of a subtlety here. I think E sub B. Okay, here, this is why. Let's go here. Let's do it this way. I'm just gonna redraw figure 728. So let's just say E sub A points this direction. E sub B is 120 degrees away from it. E sub C is 120 degrees away from both of them. So together, all three of them equal 360 degrees. Now, if I take E sub A minus E sub B, well, what does negative E sub B look like? Well, it looks exactly like E sub B, except you stick the arrow on the other end. There it is. E sub B. Now, and so this line right here is E sub A minus E sub B. I just need to remind myself why to subtract them instead of add them. Well, we'll get back to that. So what we're looking at here, though, is the fact that this guy is still 120 degrees, so this is 120 volts long. This is 120 volts long. So the only thing that's left for us to do is figure out the length of that vector, and that will tell us the voltage between these two terminals. I'm just going to call it VT for V total. And it's going to be the same as the voltage between these two guys right here. Here's your VT. And so I've got between 1 and or sorry, no. I've got it between 1 and 3. I've got it between 1 and 2. There's your VT. And now I just have to get between 3 and 2. And that's this line right here, VT. So if we go back down to our phase diagram, what we're looking for is how long that line is. And again, we could also take E sub A and subtract it from E sub C. We'd end up somewhere over here, and this would be our V total. So E sub A minus VT, sorry, I'm switching back between E's and V's, but that equals V total. This equals V total. Same thing here. There's your 120 E sub A, if we, or no, let's go down to E sub B. If we subtracted E sub A from that, it would be off over here. And this would be your V total. So there's multiple ways to do this. So you subtract the two voltages, and again, I got to go back and remember why we're actually subtracting them rather than adding them. But for now, our issue is to find the length of that vector. So let's just do that on a separate sheet, because this was getting kind of messed up. So here's your 120. Here's your 120. This guy is 60 degrees. This guy is 30 degrees. This is 90 degrees. And this has to be 120 degrees. So there are tricky ways to do this, but the simplest way is just to figure out how long this line B is. Dustin, you want to take a shot at that? Give me a formula to calculate B based on this triangle. Based on your trig. I'm using sine, cosine, tan. What's the best thing to use here? Well, let's do this. Since we know 60 is sitting right here, 120 is our hypotenuse. Are we going to use the sine or the cosine of 60? Cosine, okay. So there we go. So B equals 120, which is the hypotenuse, cosine 60 degrees. Somebody tell me cosine of 60. I'll sneak that in down here. My little cheat sheet. Whoa, that was fast. I didn't even type anything. Excel has now achieved artificial intelligence. It just read.
Destroyed.
Oh God, man, it's time to get out. Okay, it equals a half. So 120 times 0.5 equals 60. So B equals 60. And it's 60 volts. So this whole thing down here is 180. 120 plus 60. Now we need to know what H equals. What's the formula for that bad boy, Dustin? 120 times what? We already used cosine 60. Sine, there we go, thanks. 120 sine 60 degrees. 0.867. 120 times 0.867 equals, what do you got, Ryan? 80 something? No, 90? Shelly Mitchell, getting her done. 104, right? So now to get, we're just going to call this thing, well, it's V total, or C in trigonometry speak. V total just equals, so we can just use Pythagoras on this guy, 180 squared plus 104 squared equals, so SQRT 180 times 180 times that times that, close parens, enter. Hello. Oh, I forgot, I got times instead of plus. 208. volts, which is in the textbook. It's a funny little typo there. Between line 1 and line 3, they wrote 208C instead of 208V. Did you see that?
Yeah.
Kind of weird. Random. Okay, so just to review, what I've shown is that the electric field and the magnetic field are always going to be perpendicular to each other, and they're always moving. They're always changing. That's the whole point of pumping electrons down a wire. It's similar to a bicycle pedal, in that it's only on kind of half the time and in a sinusoidal manner. I showed 3 phases, showing that they're 120 degrees out of phase with each other. I showed that if you had 2 things exactly in phase and you added them, they just add geometrically, visually, no problem. We demonstrated that the cosine is 90 degrees out of phase with the sine. Did that in Excel too, that was kind of fun. Then dug a little bit deeper into this delta connection, and that's just how the 3 coils inside the 3-phase motor or 3-phase service are wired. I showed you that you could talk about normal space in 3 different ways, and I tried to jump down into phase space. And one way to think about this is amplitude sort of here, and phase is sort of there-ish. I don't know, and like how fast the thing's spinning around could be your omega. Not that easy to visualize, but this is how we can turn it into a trig problem. I kind of botched it because I wasn't all that clear on exactly why you're subtracting these and adding them. I'll try to get into the subtleties of that later. Nevertheless, to add those 2 vectors together, you just put the tail of one on the head of the other. As it turns out, we're adding the negative vector. That's why it ends up pointing in that direction. And then we just did some trig to get the magnitude of that voltage in phase space. All right. And I think it's time for 214. Woo!